Katja and Knut for so much for inviting me and give this like first Zoom lecture today for this semesters like online seminar. It's a great pleasure. And this is a talk about 3 different works which have all been finished now during this year. And this is, as you can see from the list of my collaborators, like a collaborative effort by excellence. But I really would like to give a shout out for all the younger researchers in my team, like Boya Liu, Adrian Guan, Andrew Shedlock, Lilian, and Jiao Shao. You guys really made mine and Matti's work very easy because this really is your body of work, and me and Matti were just steering the boat. But anyways, I would also like to give my note for NSF for supporting our research. So what I'm going to talk about today is seismic imaging or wave-based imaging related inverse problems. So the idea of these problems that we are doing here all the time is that we have some domain that we don't know, say the structure of the Earth or what's happening inside a human body. And then what we are trying to do, we are trying to probe inside and see what's happening there beneath by sending some seismic or acoustic wave into the medium, which will propagate through the medium and then return into some set of recorders where we receive some information about this wave. So it can be like some how long it took for the wave to come, or what is the direction the wave comes out, or something like that. So the idea here in both of these ideas is that the waves now propagate along the routes which take the least amount of time. And now, of course, what is that route now depends on my underlying geometry of the subsurface. So that's why we are going to model everything here in this talk on Riemannian geometry rather than Euclidean one, because that really like nicely captures the propagation of waves. So what we are going to do today, we are going to study hyperbolic inverse problems, which are built on top of this elliptic operator, which we call magnetic Schrödinger operator. So throughout my talk, I have basically 2 types of manifolds, MG, which is the one with boundary, and NG, which is the closed manifold without boundary. So whenever you see M, it means a manifold with boundary. And whenever you see N, it's a closed manifold. So for instance, M could be Euclidean disk and N would be Euclidean sphere. So no boundary in that one. Also in this talk now, I all the time talk about a smooth real-valued one form A and a smooth real-valued function Q. Okay, and now with these like settings, I can now define magnetic differential dA, which is now just like a generalization of the regular exterior derivative operator on manifold. So this is the operator which you can kind of identify as a gradient on Euclidean setting, but now the catch is that this D operator and also now dA do not depend on my metric, they only depend on the smooth structure of the manifold. So kind of like the key part here in this talk is this magnetic differential dA. And now, having introduced that one, we can now define this magnetic Schrödinger operator, which is now just a symmetric first order perturbation of my Laplacian on the manifold. So I define this magnetic Schrödinger operator exactly the same way as I would do the Laplacian. So I take now the magnetic differential and then I apply the magnetic divergence to this. So the same idea as getting the Laplacian, and now this will produce me this second order operator, which I can write in this form, where we see that the leading order term is exactly just my Laplacian, and then my first order term A appears here, and then my 0th order term Q appears in here. And now by this definition, this is now L2 self-adjoint operator on my manifold, and it's also of course elliptic. So it's a generalization of the Laplacian. And now what I want to study then today is now like 2 hyperbolic problems related to this elliptic operator. So on the left column, I'm looking at now the case on the closed manifold like the sphere. And then on the right hand side, I'm looking at the case on the manifold with boundary like the disk. So in the left hand side, I assume all the time that I don't know what my manifold is. So I know it's compact, but I don't know its genus. So I don't know, is it like a sphere or is it like a torus or a figure 8 or anything like that. So I have no idea about that idea at all. I just know it's some compact closed manifold. Okay, so then here I have like two sets, S and R, on my manifold, which are my observation sets, and then I study this Cauchy problem for the wave equation on this closed manifold. So what I do, I assume that initial state of each wave is just 0, and then there is some interior source F. So this now launches my wave, which then propagates through my manifold. And now what we are trying to do in this first column, well, we would like to recover my manifold, my covector field, and my potential function from this so-called source to solution map. So what I do, so I always launch waves on top of this set S. So now here I think about now waves that are launched from this small set in space-time, and then they propagate inside my manifold, and then I capture these waves on top of my set R. So I send lots of waves, which I then capture on the other set. So now a priori these sets S and R can be disjoint or have some common overlap, but both of the cases will be discussed today. So can we recover all my unknowns from this type of measurement by sending lots of waves from one place and capturing them on some other place? Then if you go to the right column, so here I'm looking at now boundary value problems. So now here in this part of the talk, I assume that my manifold is a known manifold with boundary. And then I denote by sigma the lateral boundary of the space-time of height t. And then here I look at now initial boundary value problem for my wave equation. So again, 0 initial state, but now instead of having interior source, I have a boundary source, Dirichlet boundary source on F. And then what is now my measurement? It is the Dirichlet to Neumann map for this hyperbolic equation. So what I do, I send a wave with prescribed Dirichlet boundary condition, and then I measure the respective Neumann boundary condition. So notice, guys, here that here I have this magnetic differential already appearing, which was in the previous slide. So now having this first order term now makes me change my Neumann data a little bit. And the same question that I want to ask as on this right hand side is that can I recover my A and Q, but not only uniquely, but actually even stably? Okay. And as a small disclaimer, well, this is not actually possible. So this existence of this first order term will cause us lots of trouble, but it also will make the problem more interesting. So now for the moment, let's just consider the case of the closed manifold, Ng, and magnetic Schrödinger operator over there. So let's now assume that I first have a solution for this wave equation. And let me try to retune the parameters of my operator a little bit and try to convince you that actually my measurement does not change. And how do I do the retuning? So let's choose some complex valued function kappa, which is smooth. It's always unitary. And then if I now do this kind of conjugation to my my magnetic Schrödinger operator, I arrive to a new type of magnetic Schrödinger operator where I actually just add this kind of a closed one form here in addition to my A. So doing this conjugation by direct computation, you can see that it just changes my magnetic potential by this closed form over here. Okay, so now what I can do, I can now, okay, like let's see that if you solve this equation, then I can actually show by direct computation that kappa of u will solve this new wave equation, but I have to multiply my source f also with kappa. Okay, so now if I do an assumption that, okay, let's say that my kappa is 1 on the set where I send waves and 1 on the set where I receive waves, then this equation holds true. So all my waves, all my sources look exactly the same as they used to be. And now, because I do only the recording on the set R, so then also my solutions look the same. So what is the conclusion here? I can do this kind of a global change, kappa, which is not detectable from my measurements if my S and R are not the whole manifold. So there is this kind of a invisibility. And something similar is also true in the case of a manifold with boundaries. So now for easy situation, let's just think about my manifold would be simply connected with boundary. So then I can actually write my kappa in this kind of a form, where phi is some compactly supported function, a smooth function on M. And I can notice that, okay, so now in this case, this conjugation would look something like this. And now we notice that, okay, here actually, if we go back to the kind of like integral geometry class, notice that here this new vector field which I created here falls exactly in this kind of a situation of Saraf-Futinov's, which says that any vector field I can decompose into solenoidal part AS and a potential part d phi. Okay, so this solenoidal part is divergence free, and then this potential part is now this differential of some function which vanishes on the boundary. So what we see here in this question here, that again, like I have basically freedom of changing this part however I want, and my measurement does not change. The Dirichlet Neumann map in this case would not change. So what is the conclusions what we can see already from here, that in this case of closed manifold, I can only recover my magnetic potential up to this gauge transformation from the respective source to solution map, or in this case of a manifold with a boundary, I can only hope to recover the solenoidal part of my magnetic potential. So having this first order chain means that there is always something invisible which I cannot hope to recover. So, but what we are aiming to really do in this talk, we are going to study 3 different inverse problems where 1 and 2 are related and 3 is then a bit different. So in 1 and 2, in both of the cases, I'm studying now this closed Riemannian manifold NG. But in the first problem, I'm now assuming that I'm sending the waves at the same set where I receive them. And now I'm claiming that in this case, this local source to solution operator determines everything, the manifold, the vector potential up to this gauge, and this zeroth order potential. Okay? But then the question, so this is kind of the situation as in this ultrasound imaging. So in ultrasound imaging, I'm sending and receiving the waves at the same location. But now if you look at the situation as in that seismic prospecting, I'm actually sending the waves somewhere else where I receive them. And now I'm claiming that, okay, let's say that if my sets S and R where I send and receive waves are disjoint, then with some extra assumptions for my receiver set, which doesn't actually depend on my lower order terms, I can recover these lower order terms again from this source to solution map up to this gauge that I just talked about. Okay, so 1 and 2 are very much related to each other, and number 3, which is now about this manifold with boundary, is quite different. So here I'm studying now, can I recover these lower order terms somehow stably, and in particular Hölder stably, from the hyperbolic Dirichlet Neumann map under some assumptions. So first assumption, that my manifold would be simple. So for these purposes of this talk, we can just think about that simple is something exactly similar as a convex smooth bounded domain in Rn. Okay, and then what I want to need to do some a priori assumptions. I need to assume that my A and Q are somehow uniformly bounded in high enough Sobolev sets. So under these 3 assumptions, where 1 is geometric and 1 are just like saying that I'm looking at stuff like in some ball, like I can recover things actually even stably. And how are we going to do these 3 things? So what is like the underlying the red line which connects them both is that we need to do some kind of a trick which reduces this PDE-based inverse problem to a geometric inverse problem, and then we solve this geometric inverse problem. So really this talk is about reductions. So I'm trying to show you a couple types of reductions that we need to incorporate to solve these problems. And now the rest of the talk will be that I go through each of these problems more carefully and try to say something about the proofs, but I might need to skip some of the parts in the proofs for the lack of time. But maybe here I ask if you guys have any questions. Okay, and please, if you have any questions at any time, just unmute yourself and ask. I'm not able to see any comments, or if you raise your hand, just speak over me. That's completely fine. Okay, so let's first go to this question where I'm trying to now recover everything uniquely, having the sources and receivers in the same set. So I'm looking at this kind of a situation like here, that now NG is a complete or closed Riemannian manifold. Either is actually fine. And then there is this measurement set X, which is now the same as S and R together. So X is now S and R. So I'm looking at this, and this is kind of the idea that this is the part I know, and this set can be very small as long as it's open, and then there is some like unknown part of the manifold which can have like very, very funky geometry or whatever. So what I'm doing here all the time, as in this slide earlier, I'm looking at this hyperbolic Cauchy problem where I send waves from this set X, but now I also capture the waves in this set X. So my question is, can I recover everything up to this gauge that I mentioned now by this type of measurement when I send lots of waves and I capture each of them? Okay, so what is the problem set up like more concretely? So assume that I have two copies of everything. I have two Riemannian manifolds. I have two smooth covector fields, two smooth real-valued functions, and each of the manifolds have their respective observation sets. Okay, and then now all these four first things now then gives me the respective source to solution maps for this respective hyperbolic operators. Okay, so now let's try to first ask, like, what do we mean that these data are the same? So what does it mean that now these two set of manifolds with lower order terms would have the same data? And we've formalized it in this box over here. So we now need to a priori assume that there is some a priori known diffeomorphism between my observations at x1 and x2, which I can promote into a diffeomorphism in space-time by this like a trivial trick. And then I'm asking like now kind of a question that, okay, do I have the same wave if I first change the coordinates and then solve the wave equation and record the wave, or if I first solve the wave equation and then do a change of coordinates? And these two things should be the same. And if they if they are the same, then I say that my data are equivalent, or these source to solution operators are the same. So the question is that if these source to solution operators are equivalent, then are my manifolds diffeomorphic, and all these terms arising in my BDE, are they equal up to change of coordinates and this before mentioned gauge? And the answer is of course yes. Otherwise it would be a bit boring job. So what we did with my PhD student Andrew Shedlock like earlier this year, we showed that yes, exactly, actually this kind of a gauge that I described is the only possible. So if I have this a priori known diffeomorphism, which makes my source to solution operators equivalent, then I can promote this local diffeomorphism into a global one, and I can construct this smooth function kappa in such a way that it's 1 on the observation set, it's unitary elsewhere. My metrics are given by pullbacks. My magnetic potentials are given by pullback of the first one plus this gauge that we talk about. Sorry, here should be Q. So my Q1 and Q2 are also the same. So the catch is that yes, you can recover everything as long as you send and receive the waves in the same set. Okay. And how do this kind of a proof work, and where does it build on? Well, we build on this like celebrated boundary control method, which I try to survey here in these next two slides. First, in the case with manifold with boundary, and then in the next slide on the manifold which is closed. So I look at this source to solution operator. So in the case of manifold with boundary, my data is given by the DNF. So first, it was shown by Belishev that in the Euclidean setting, you can recover the lower order terms or lower order terms if you measure everywhere. Then Belishev and Kurilev pushed this theory further on the Riemannian manifolds, and then they studied the question where you have no A's and Q's. So can you recover everything if you do measurements everywhere on the boundary? And the answer is yes. And then Katsulev and Kurilev look at the case where you do the same kind of a setting, but now you allow lower order terms, and you only look at the measurements that you see, your Dirichlet data is supported on S, while your Neumann data is also measured on the same set. Okay, and then a couple of years later, Lassas and Oksanen showed that okay, so actually you can let go this assumption that you send the waves in the same set where you receive them if you have some extra assumptions. And I will talk about these extra assumptions also later today. And also then
Kian, Kurilev, Lassas, and Oksanen showed that, okay, so let's say that you know that metric is already recovered. Can you do the same for the lower order terms under, again, similar extra assumptions in the case when the sets are disjoint? Okay, so this is like the history of stability and history of uniqueness. And then question about stability. So how many, like what kind of works there are which are built on this boundary control like regime and gives me stability. So there is like a couple of works on that, but maybe the most recent one is by Burako, Ivanov, Lassas, and Lu, which show that, okay, so you can actually recover your Riemannian manifold with boundary only double log stably. So this method is very good for providing uniqueness, but not very good in this stability case. So I think the conjecture at the moment is that it would be at best logs type stable, and double log is now just an artifact of the method of the proof. So I'm challenging you guys to get rid of this double over here. Okay. So then about the manifold, when I look at the closed manifold, when I don't have the boundary and my measurement is local source to solution operator. So this kind of a setting has not been studied so extensively as the case with the boundary. So the first work that I know about this case is the one I did with Tapio, Helin, Matti Lassas, and Lauri Oksanen in 2018, where we now did not have lower order terms, but assumed that I send the waves in the same set when where I receive them, and we showed that yes, you can recover the geometry uniquely. And then now, like very recently, Lassas, Nursultanov, Oksanen, and Ylinen showed that, okay, so again in a case that if your sets where your measurements are done are separate, then you can recover the geometry, but with some extra assumptions. Also, there is some stability result related to this direction by Bossi, Kurilev, and Lassas, where they again prove this kind of double log stability for recovering of the metric with no lower order terms, and very recent paper by Jingpeng Lu, where he again proved this double log stability for both metric and the potential Q, but I don't remember that in his paper there is no first order term. So what we see here in this kind of a paradigm, that whatever like measurement I look, is it the source to solution operator or the DN map, like this disjointness of the data is a huge issue. It's like really like not solved that like without quite strong geometric assumptions. So again, I challenge you guys, like try to prove this kind of like result like without assuming these extra assumptions, and this would be a huge breakthrough in our field. Okay, so let me go to these like proofs, how do these work, and I maybe spend now a bit more time on the first proof, because these methods that are presented in there will propagate also in the second proof, but I might be then more brief on the second one. But let's start like what is the idea? Like the idea again is that we want to reduce this PDE based problem to a geometric one, and let's try to go through the key things that we need for this reduction. So the first thing is that my waves somehow has to behave very nicely, and they must now somehow move in a speed which is corresponding to my Riemannian distance function. So in some sense, like what I want, what is the most geometric thing ever? Well, distance. Well, I now need to make a case that my waves propagate according to velocity related to this distance. So what I mean by this, so if I now look at again a wave equation, and just having an interior source, and now if this interior source, it's supported in this blue set in my space-time cylinder, okay? So then what's going to happen, now all the waves will start to propagate at the speed of light, at speed of light, which now means that if I let my time go from 0 to t, then the largest area where my wave might not vanish is given by this domain of influence, mxt, which is now just a closed metric ball around my set x where I send the wave. So no wave can move in time t like outside this set mxt. Okay, so then there is kind of like the complementary result like that. So this previous result showed what is the largest set where the wave might live, and this is kind of saying what is the largest set where the wave must die. Okay, so let's look at this. So we are looking at now some open set y and measurement time t. And let's say that I solve the wave equation in my whole manifold, and I know a priori that my wave needs to vanish in this kind of a cylinder over here, okay, in space-time. So then the question is like, okay, so what is now the largest set where the wave must be 0? So what is the largest set where this data now says that the wave is 0, and it's actually given exactly by this double diamond over here, whose definition is given by the red line above. So this is the set where the wave must vanish and will vanish, but then you can actually show that here outside this wave might not vanish. So this is kind of sharp in this case. And something I want to mention about this result is that this is really depending on the fact that this all my coefficients, metric G, vector potential A, and my scalar potential Q are all time independent. So this result is known to break if some of my coefficients depend on time. So this is kind of like why in this regime we have to limit our attention to time independent coefficients. Also, this is the reason why in some of these earlier places you at least have to introduce log type of instability. So this is kind of, if you want to build on unique continuation, then some kind of a very strong instability will appear because of this. Okay, so what can we get from this, like this unique continuation? So we can obtain this kind of higher order approximate controllability result, which now can be stated in such a way that if I think about now, say, some Sobolev space HK, and I look at now the domain of influence at time t, which is now expanded from my set X. So then I know by this already by this finite speed of propagation that all of my waves needs to live in this set. Okay, but now what is the what we can conclude now by combining the this finite speed of propagation with approximate controllability, that this set of waves is actually dense in this space. So it's not only subset, it's actually a dense subset in this. And now, of course, if I take my Sobolev index k here high enough, then I can actually show that there exists non-vanishing waves. So I can show that if I take any point x from my space, and then I look at like that it just has to be t close to my set where I send wave, then I can show that, okay, there exist actually waves which do not vanish at this given point. And this is like important thing for our web. Okay, so this was kind of like told us how the waves propagate. So then the important question is like, okay, how do I actually gain information from outside my measurement set? So everything is now measured in this case on this one space-time cylinder. So how do I see outside of that? And this is given by this Plakova-Chensky identity. So this is some nice identity which only basically comes from integration by parts. But here is the crux. Like in order to prove this result in this formula that we see here, I need to know that my elliptic elliptic operator here is self-adjoint. So here is a one key piece. Like to prove an equation like that, I need some kind of self-adjoint property for the elliptic operator. So what does it say? So it basically says that if I look at two sources and look at the waves of these two sources at some time t, so now I can compute their L2 inner product by just using stuff what I already know, EA, the source to solution operator, and then these two operators R, which is a time reversal, and then this J, which is this compressing operator or something like that. So the catch here is that now the right-hand side of my equation is computable, and it only depends on my known parts, while the left-hand side contains information outside my set X. So this contains information also far away from set X, and this is what I really want to like use to kind of get towards the solving the inverse problem. So in particular now here, if I now replace everything with these decorated versions, so and if I know that these two operators are the same up to this equivalence I told you about, I can now notice that actually two waves with a common source have the same magnitude. So these are like solution for the wave equation with the coefficients 2, and this is the solution for the wave equation with coefficient 1. So this block of a change guarantee now actually tells me that in this case, when I send and receive the waves in the same set, I actually have equivalence on the magnitudes of the waves also. Okay. So what is then now the idea from here onwards? Well, we need to use those four tools to kind of reduce this problem for something very geometric, as I said, like, and what is more geometric than travel times. And what do I mean by this? Well, we need to be somehow say that when I'm sending waves from this set, I can now find the distances from any point here in my set X to any point inside my manifold. And this is what I call the travel time data. So the boundary control method converts that that TDE-based problem to this kind of inverse problem for this travel time data. Do I know for every point P the distance to any point in X? And if that's the case, then we showed by with Heli-Lassas and Oksanen that actually, yes, in this case, you can recover your Riemannian manifold up to change of coordinates, and this change of coordinates actually corresponds with my a priori known data map file. Okay, so this is kind of the idea. You want to use those tools to reduce the problem here. And that's the end of this part. So any questions about that part? Okay, so now here the catch was that we had no assumptions on my set where I send and receive the waves. So now let's look at the case where I have this disjointness in the measurement set. So again, I'm looking at closed Riemannian manifold, and there are now two disjoint open sets. So S and R, S like sources, R like receivers. So if I describe these sets now on, say, on an Euclidean sphere, they could look something like this. So one of the sets could be quite large, while one of the sets could be quite small. And actually now both of these pictures here, what I describe here, are actually valid, like we can prove the uniqueness in these situations, but I talk about that later. But now the catch is that these sets would be disjoint. So again, we are looking at this hyperbolic Cauchy problem. We are measuring the local source to solution map, but now really sending waves from S and capturing them on top of R. So the question, can we recover now in this situation, now the lower order terms A and Q? And the answer to this is of course yes. And this is now true under certain geometric assumptions. So what are these geometric assumptions? So now I need to do something something like more stronger geometrically than earlier. So first of all, I need to assume that my set R satisfies two conditions. So geometric control condition on the set R, which now means that every unit speed geodesic in NG reaches this set R in time t, which is how long I measure. Okay. Also, this set has to be somehow symmetric with respect to distance functions. And what do I mean by this? So if I take any point X in N, then this needs to have now some local neighborhood U in such a way that if I take any 2 points in that neighborhood, then I can find 2 points in my receiver set where P is, say, closer to Z than Q, and P is closer to Q than Z is closer to P than Q, and Y is closer to Q than Z. So if you think about when this situation could be true, so now if your complement of R would be contained in a convex set, then you just connect now P and Q by line connecting them, and then one endpoint of that line would give you Y, and the other endpoint would give you Z. So something like this type of condition. And then what we proved like very recently, so this is actually something that we published in arXiv like yesterday, that if I have now a manifold where I know the geometry, and I know that this receiver set satisfies these two geometric conditions, which by the way are independent of my A and Q, then if my source to solution operators are the same, then my zero order terms are the same, and there exists this smooth unitary function kappa, which is 1 in this set of where I send and receive waves, and my magnetic potential satisfy this equation. So now, in comparison to the earlier work, we really need to have more and stronger geometric conditions. So let's talk about these conditions a bit, like how they can be satisfied, and like what is the implication of these conditions. So why these are the good conditions? So as I mentioned earlier, so when could we say that these conditions are true? So for instance, if you look at now the first picture here, this picture here, so my manifold N is now just a two-sphere, and now I say that my R set is very large. So now here my R set is something larger than a hemisphere, okay? Which now means that the complement of R is actually a simple manifold, because any set smaller than hemisphere is simple as long as it has convex boundary. So this kind of a setting, for instance, would satisfy both of these conditions, because now if you think about any great circle, which would go here on the upper hemisphere, well, it has to come and hit my lower hemisphere also. In particular, it has to touch my set R. Okay, so my A1 condition is true. And now again, like in this setting, as I said, like my situation is convex. So if I take 2 points and connect them by a great circle, then one end of this great circle is closer to P than Q, and vice versa. So both of these conditions are true in this left setting. But also, like what we can actually see would be true in this kind of a right picture, like without like assuming such a large R, we can actually show that if this R is a set that contains a curve connecting to antipodal points, then actually this would be enough. So this would satisfy now automatically my geometric control condition, because again, all great circles will need to meet this set R, but also by a rather simple proof, but really relying on the symmetry of the sphere, we can show that this other geometric condition would be true in this case. So this could be like, for instance, 2 example cases of 2 example measurement settings where this recovery of the lower order terms with this disjoint measurement would be true. Okay, and why do we want to put these assumptions? It's because of if we have this geometric control condition A1, then that implies that my control operator of my Cauchy problem is onto. So in particular, my Cauchy problem is exactly controlled. And what does this mean? So this control operator is now the one where I take now the source for this equation, and then I measure the end state and end velocity of my wave. And now this control condition, if that's true, then it's well known that then this operator is onto. Okay, and why do I really need to have this kind of a condition is really because I will lose something in in this disjointness. So again, we can prove Plakover-Chensky identity, which now look effectively very similar as in the previous slide, previous case. But now the difference here is that now here my 2 waves, one of them has to have a source on top of S, while the other one has to have a source on top of R. So remember, in last case, I had the F and H both in set S or R, say, but now here, like I need to have them in these 2 different. Okay, so what do I have here? So if my source to solution operators are the same, then what I can have here is now that the inner product of all these type of waves, where one is sent from S and the other one is sent from R, equals to their siblings. Okay, but now what do we lose? We lose the equivalence of the normals. So here, because F and H are sent from different sets, I cannot just say F equals H, and I cannot have this kind of a control over here. And this is really like the key that I need to somehow compensate, which I now have lost. And how I compensate that is now exactly using that exact controllability that we will have. And I unfortunately need to skip the proofs in there. But we lose the control, and to compensate, we use the exact controllability. That's the long story short. Okay, so let's quickly, I think I have 10 minutes. Let's talk about this last problem. And this is now the different one, because here we are looking now manifold with boundary. So here we are looking at now, let me just recall, a magnetic potential A, which is smooth, but whose now Sobolev norm, K Sobolev norm, is bounded from above by some known constant capital K. The same thing for the 0th order term, but I know it's again bounded, but it's W1 infinity norm is now bounded by K. Okay, and then what I'm looking at here, I'm now looking at my wave equation in space-time Q, which lateral boundary is sigma, and then I consider this boundary value problem now for this case. 0 initial conditions, no interior sources, and then I just plug in a boundary value there. And what is my my measurement now? It is this hyperbolic DN map. But now I'm in this project, I unfortunately need to look at like very rough boundary sources. So some sources which are only L2. And now what I then need to do, I now need to then define my direct to Neumann map, my hyperbolic direct to Neumann map in a weak sense. And the definition is given by here, where I use this like a solution for the adjoint problem. So the problem where I have here the terminal state. So this is now the weak formulation here. So the goal in this part is now to recover my solenoidal part of A and this vector, this electric potential Q stably from this DN map. Okay, so what we obtained this summer by with Boya, Liu, Hadrian, Guan, and Lilian is that now if I look at simple Riemannian manifolds and assume that this K is some large number, then if I have now two magnetic potentials which live in this case, so we require this kind of order of Sobolev regularity or this kind of level of control in the Sobolev norm in order to use Sobolev embedding and have like a continuity. And here now we look at these Qs in the same set. So if we now have the situation that these unknowns that I want to recover stably agree on the boundary, and if I measure long enough, like say the time is at least the dimension of the manifold, then we can show that there are two constant C and sigma, which only depend on my manifold, which I assumed I know here, in this case the simple manifold, such that the following Hölder stability estimate holds for the recovery of these lower order terms. So here pi, let me just recall, this is now the hyperbolic DN. Okay, so we can recover stably, Hölder stably, these lower order terms now if my manifold is seen. And I hope I can get that part, that I can explain why we need the simplicity. So this proof is actually quite very different in comparison to these earlier works, which talk about this boundary control method. So this is kind of very different approach. And let me recall some history of this. So Ben June, for instance, like studied like this similar problem in Rn and showed like Hölder stability for the lower order terms in this set. And really like the paper, which probably was our motivation to study this problem, is this very nice paper by Bela Su and Dos Santos Pereira, where they didn't have the magnetic potential, and they proved exactly similar type of Hölder stability result as we did now on simple manifolds, but only for the scalar potential. Okay, and maybe I would like to just mention something about this last work over here, which is very interesting in the sense that, okay, you can actually do better than simple manifolds. So by this work by Arne and Guillermo, they showed this kind of similar result as Bela Su and Santos Pereira on these manifolds which have a hyperbolic trap set of geodesics and no conjugate point. So this is kind of a set of manifolds which extends to simple manifolds. It's not all manifolds, it's an extension of simple manifolds. So really kind of interesting that the simplicity is not absolutely necessary. But now what we see here is kind of like a difference that here, like with this kind of strong geometric assumptions, we are able to prove this kind of like nice regular stability result, while in the earlier works, like which rely on this boundary control method, you can only prove log or actually at the moment double log type of stability. So here it is like kind of like looking at better geometries really help. Okay, and how do we actually now use these better geometries? So it's kind of like condensing this one slide. So if we only look at now the case where we want to now say recover the leading or like the higher order parts, the solenoidal parts of my magnetic potentials, then what I want to do, I want to reduce this problem now for the invertibility of the geodesic ray transform. So let's recall what is this. So I'm now looking at now my one form A, and then I take a geodesic on my manifold, which starts at point X on the boundary, pointing to direction psi, and then because my manifold is simple, it will exit at some time tau. Okay, so this gives me now effectively a line integral over this magnetic field when I contract that against the velocity of my geodesic. So for each x and psi, this is a number. So what do we get here is now, if you read the book of Sarafutino, for instance, that this operator, now a priori defined for smooth vector potentials, can be actually extended for L2 smooth vector potentials. And this would be a bounded operator between these two L2 spaces, where here this is now the inward pointing sphere bundle on my boundary, where I need to put this kind of a weight here. So in particular now, if this I is bounded, so then I can compute its adjoint operator, I star, and furthermore, the normal operator, n, by composing these two operators. And again, this is a bounded linear operator. Okay, and now what we really need to prove our result is a stability estimate for this normal operator here, which was proved by Stefanov and Ullman now 20 years ago. So really what we need to do is to construct some special solution which look like GGO solutions, and then use them with some integral identity to reduce this problem now for this stable inversion of this X-ray transform, which is known in a simple manifolds, and then also in some cases in this like hyperbolic trap manifolds. And that's the idea. So the difference really is that we reduce this problem not to distance functions, but to this problem on X-ray transform. And I think I stop here. Thank you so much.
Thank you very much, Teemu, for the very nice talk. Are there any questions or comments, please? Any questions or comments, please? Please feel free to unmute yourself. Any questions or comments, please? Okay, if not, thank you very much, Teemu, for the very nice talk once again. Thank you very much, everyone, for coming. Thank you.
Thank you so much for having me, Katja.